welcome again in this lecture of the two-dimensional equation. Today I am going to solve those questions of the Laplace equation in which either the two boundary conditions are non-zero or the questions related to the infinite plate in which one boundary condition is non-zero. So in type 2 we have those questions in which with finite plate with two non-zero boundary condition. In this case, we have a finite plate with two non-zero boundary condition. So let us solve a question of finite plate find the steady state temperature at any point of a square plate and the square plate is finite if two adjacent edges are kept at 0 degree centigrade and others at 100 degree centigrade. So find the temperature if the two adjacent sides are kept at 0 degree centigrade and others at 100 degree centigrade. So here solution, here so this is your x-axis and that is your y-axis. Suppose that the length of the square plate is L, then it is given that this is your 0 degree centigrade. Now if the length of the square plate is L, then again the adjacent side has temperature 0 degree centigrade and the other side 100 degree centigrade. So this is your at 100 degree and the temperature of this edge is 100 degree. So here you can see that we have two non-zero boundary conditions, one at x equal to L and the other one is at y equal to L. Because the length of the, suppose that the length of the square plate is L, then suppose that the length of the edge of the square plate is L, then at this edge your temperature is 100 degree centigrade and again for this edge your temperature is 100 degree centigrade. That means we have two non-zero conditions and two zero conditions. Now to solve this question, let us split our solution in two cases. As we have two non-zero boundary condition, so let us split our solution as uxy equal to u1xy plus u2xy. Now our u1xy is the solution of your Laplace equation. Steady state solution means the solution of the Laplace equation. Now u1xy will be the solution when the temperature of this edge is 0, and in that case we will have three edges with 0 degree centigrade. And let us assume u2xy is the temperature. Let us assume u2xy is the solution. In that case, when your temperature of this edge is 0 and the temperature of this edge is 0 and the temperature of this edge is 0. That means u1xy is the solution when three boundary conditions are 0 and u2xy is another solution when your another three boundary conditions are 0. So that we can apply the solution of the Laplace equation. So where u1xy is the solution of Laplace equation with boundary conditions. Say u1 when your y is 0, say the temperature is 0. Say this is your first condition, and then again when your x is L, that means the temperature of this vertical edge. When your x is L, again your temperature is 0, and in the third case, when your x is 0, again your temperature is 0, and suppose that the temperature of the upper horizontal edge is non-zero in this case. So the upper horizontal edge means when your x is fixed for this, when your y is 20, so suppose that your temperature is 100 degrees centigrade. So in first case, let us assume u1 is the solution of the Laplace equation with this boundary condition, and u2 xy is the solution with boundary conditions. Say first one is ux0 equal to 0. Second condition is again when your, now the first condition is when your x is 0. Then I am assuming the second condition when your x is 0. That means when your x is 0. And in the third condition I am assuming when your y is 20. Again let us assume this is your 0. And the fourth condition, that means this particular temperature, the temperature of this particular line, that means when your x is 20, your y is 100 degrees centigrade. That means consider the following three diagrams. Initially, we have given that, say this is your x, this is your y. Initially, it is given that temperature of this edge is 0 degrees centigrade, temperature of this edge is 0 degrees centigrade, and temperature of this edge is 100 degrees centigrade, and the temperature of this edge is 100 degrees centigrade. We have split our solution in two parts. In the first part, let us assume our solution as u1, and for that the temperature of this edge is, let us assume the temperature of this edge as 0, and the temperature of this edge as 0, and the temperature of this edge is 0, and the temperature of this edge is 100 degrees centigrade, plus let us assume the temperature of this edge as 0 degrees centigrade, again the temperature of this edge as 0 degrees centigrade, and the temperature of this edge as 0 degrees centigrade, and the temperature of this edge 100 degrees centigrade. And suppose that the solution at any point is u2. So here you can see that your boundary conditions for u1 are when your when your y is 0, that means for this x-axis, your temperature is 0. When your x is L, that means for this vertical edge, your temperature is 0. And for this vertical edge, when your x is 0, again your temperature is 0 degrees centigrade. And when your y is 20, your again temperature is, y is not 20, y is your length is L. Length of the edge is L, not 20. Again, for this edge, your length is, when your length of the edge is L, then again the temperature for this edge is 100 degrees centigrade. And for the second case, let us assume u2 is the solution of this particular case when your boundary conditions are when your y is 0, the temperature is 0, when your x is 0, temperature is 0, when your x is L, your temperature is 0. When your y is L, your temperature is 0, but when your x is L, your temperature is non-zero. So on combining this case, we will get the solution of this particular case. That means when we have two non-zero boundary conditions. So let us find out the solution for the first case, and then on interchanging the role of x and y, we will get the solution for, here you can see that on interchanging here you can see that for this case your y is, when your y is L, your temperature is 100, and here you can see that when your x is L, your temperature is 100 degrees centigrade. So let us solve the Laplace equation for the first case, and for the second case we will interchange our x and y. So for this u1, now as in our previous lecture, the solution for this on applying the first, second and third condition, on applying as in previous lecture, or we can solve it. Solution of Laplace equation is, the solution of Laplace equation was your a cos lambda x plus b sin lambda x, or c e power lambda y plus d e power minus lambda y. Now if we use this boundary condition ux 0 equal to 0, that means when your y is 0, so on using this boundary condition we will have a cos lambda x plus b sin lambda y, b sin lambda x, as our y is 0, so we will have c plus d, as this cannot be 0, so we will have d plus c equal to 0. So from here c plus d equal to 0, or we can say that d is minus c. So let us use the second boundary condition. Now let us use the boundary condition as u1 0 y equal to 0, or u1 l y equal to 0. So this boundary condition, that means when your x is L, your y is 0. So on x equal to L, we will have a cos, not, we will use this condition later on. First use this condition, u1 0 y equal to 0. So that means when your x is 0, your u is 0. So on putting x equal to 0, we will have a into c e to power lambda y plus d e to power minus lambda y. Again, as d is in terms of c, so this c cannot be 0, otherwise your solution will be 0. So from here we have a equal to 0. Now let us use the boundary condition number 2. So on applying this boundary condition, in the left hand side we will have 0, and as our a is 0, so we will have b sin lambda l. Then in the bracket we will have c lambda y plus d e to power minus lambda y. Now here you can see that again d is in terms of c, so this constant c cannot be 0, b cannot be 0, because if c is 0 and d is equal to minus c, so this whole term will be 0. So this is not 0. B cannot be 0 because a is already 0. So if b is 0, then this solution will become 0. So from here we will have sin lambda l equal to 0. So this can be written as sin n pi. So that means your lambda is n pi upon l. So we have the value of lambda, and again, so your lambda is n pi upon l. So our solution will be, thus our solution is, therefore solution is, now your a is 0, b is there, and d is minus c, so this will be your b into c sin lambda x e to power lambda y minus e to power minus lambda y, because d is minus c. So your general solution is, or this can be written as b into c sin lambda x into sin 2 times sin hyperbolic lambda y. Now this 2bc sin hyperbolic lambda y. So your general solution is, for the general solution we can replace your constant b, 2 times bc as bn, or say capital Bn sin lambda was your n pi upon l, so this will be n pi x upon 20 sin hyperbolic n pi y upon 20. So this is your solution. So this is the solution of this Laplace equation. Now let us use our fourth boundary condition. So on applying the fourth boundary condition, that means because your u x, and then when your y was L, the temperature was 100 degrees centigrade. So on applying this condition, that means when your y is, this was your not 20, this was your L, because the length of the strip is L. So on applying this boundary condition, In the left hand side we will have 100 equal to Bn. Now if your y is L, then this will be your sine hyperbolic Ny, sine hyperbolic n pi, and here we will have sine n pi x upon L. Now if you take this one as Bn, then this is your half range, of course sine series, where my Bn is Bn sine hyperbolic n pi. Now you can see that this is your, in the right hand side, this is your half range sine series, and in case of half range sine series, our Bn is 2 upon L, 0 to L, fx means your 100 into your sine n pi x upon L dx. So on integration, this will give you integration of sine will be your cos n pi x upon L, then L upon n pi, and then the limits from 0 to L. So this will be your L upon n pi, so we will have 200 upon n pi, and in the bracket our lower limit will be plus 1 and the upper limit is minus 1 for n. And you can see that if your n is odd, then this will be your 2 times, and if n is even, then this will be 0. So this is your 2 times, so we will have 400 upon n pi. So this is when your, if n is even. So sorry, if n is odd. So our solution in this case will be, therefore your uxy is equal to Bn. Bn is 400 upon n pi when your n is odd into sine n pi x upon L into sine hyperbolic n pi upon L. So this is your solution, that means your u1. This was your u1, not uxy. This was u1. As we know that the second boundary condition is exactly similar to the first one, except for the fourth boundary condition, where your, now your y is, for the fourth boundary condition, your x was 20, your x was n, and y was fixed. So similarly, for u2, we just have to replace interchange our x and y. Similarly, for u2, our solution is, for this we will have to interchange your x by y. So on interchanging x by y, this will be our solution. So the value is fixed, so as this value is fixed, so this will be your solution. And I think there is again some mistake. This was your Bn, so this is your Bn, and the capital Bn will be, and capital Bn will be from here, our capital Bn, small bn is Bn into sine hyperbolic n pi equal to 400 upon n pi. So from here your Bn will be 400 upon n pi into sine hyperbolic n pi. So here we will have another term, n pi into sine hyperbolic n pi. So this is equal to 400 n pi into 1 upon sine hyperbolic n pi into sine n pi x upon L sine hyperbolic n pi y upon L. So on interchanging your x and y, you can see that your Bn is independent of any x and y. Bn does not have any term of x and y. So for solution y2, for solution u2, we will have same constant Bn. So the constant Bn will be 400 n pi upon sine hyperbolic n pi, and for this solution, this will be your n pi y, and this will be your n pi x upon n. So now let us consider the third case, type 3, when we have infinite plate with one non-zero boundary condition. Consider this fourth case, when we have infinite plate with one non-zero boundary condition, and let us solve a question. A rectangular plate with insulated surface, or rectangular plate with insulated surface is 10 centimeter wide and so long compared to its width, and so long to compare its width, and it may be considered infinite in length, without introducing appreciable error. Without introducing any appreciable error. So find the temperature. The temperature at the edge, at the short edge, y equal to 0 is ux20 equal to 20x into 20 10 minus x, when your x is between 0 to 5, and then when your x is between 5 to 10. So the length of the short edge is this one, and all the other edges are kept at 0 degree centigrade. Find the temperature uxt at any point and subsequent time. So solution, here you can see that your short edge, that means y equal to 0, has non-zero temperature, so it means as your short edge is y equal to 0, means that is your x-axis. If this is your short edge, then hence our long edge is parallel to the y-axis. Short edge is your x-axis, so you can see that your long edge will be parallel to the y-axis. So here you can see that this is your short edge, which is your y equal to 0, and this is your long edge, and the width of the insulator surface is 10 centimeter. And now you can see that your long edge is parallel to the y-axis, and again you can see that the long and wide, and here you can see that your rectangular plate with insulator surface is 10 centimeter wide and so long compared to its width, and you can see that the length of it is very large, so we can take this one as infinite. So let us assume this one as infinite. So that means, and the temperature for this surface is your infinite. So that means when your y is infinity, your temperature is 0. Again, when your x is 10, your temperature is 0. And when your x is 0, your temperature is 0. And when your x is 0, your temperature is, when your y is 0, your temperature is non-zero, say fx. So these are the boundary conditions. When your y is 0, your temperature is given as non-zero, which is your, say this one as fx, And when your length of the strip is 10 centimeter, then your temperature is given as 0 degree, and here we have given 0 degree. And in this case, when your length of the rod and when your rectangular plate with the insulator surface is 10 centimeter wide and it is long, that means the length, when is length has infinite, then your temperature is 0. So now let us solve the problem of Laplace equation for these 4 boundary conditions. So now solution of Laplace equation is solution of the Laplace equation was uxy equal to c1 or a cos lambda x plus b sin lambda y, b sin lambda x, then c to power lambda y plus d to power minus lambda y. Now let us take the boundary condition one by one. If you take this boundary condition, that means when your x is 10, y is 0, or when your x is 0, y is 10. If your x is 0, y is non-zero, then your temperature is 0. So on applying this boundary condition, we will have a cos lambda x plus b sin lambda x. So from here you can see that as your x is 0 and your x is 0, so we will have cos 0 is 1 and sin 0 is 0. So we will have a into c to power lambda y plus d to power minus lambda y. So from here you can see that your a is 0. Now if we apply the second boundary condition, when your y is infinity, your u is 0, so we will have 0 equal to, as y is infinity and a is 0, so we will have b times sin lambda x. As y is infinity, so we will have e to power minus infinity, e to power minus infinity is 0, so we will have e to power lambda y, and the value when your y tends to infinity. Now again this term cannot be 0. Again this term cannot be 0 and b cannot be 0, otherwise this solution will become 0. So from here you can see that your c will be 0. A is already 0, so we cannot have b as 0. So b is non-zero. E to power lambda y cannot be 0, so this c will become 0. So we have a and c as 0. Now if a and c are 0, then use the third boundary condition. That means when your x is 10, your y was 0. So if your x is 10, y is 0, then we will have b into sin 10 lambda. Then here we will have d into e to power minus lambda y. D cannot be 0, otherwise this solution will become 0. So from here your sin 10 lambda will be 0, which is your sin n pi. So lambda will be n pi upon 10. So your lambda is n pi upon 10. Thus our solution is uxy equal to a cos lambda x. A is already 0, b is non-zero, so we will have b, and from here we have the constant d. So our solution will be b into d sin lambda x into e to power minus lambda y, and the general solution is uxy will be summation bn sin lambda was n pi upon, I think, 20 or 10, n pi upon 20, n pi upon 10 into x, and e to power minus lambda. Lambda was your n pi upon 10 y. So this is our general solution. Now let us apply the fourth boundary condition. In the fourth boundary condition, your y is 0 and the value of this ux naught is fx, which is equal to 20x when your x is between 0 to 5, and then it was your 20 into 10 minus x when your x is between 5 to 10. So now let us apply this boundary condition. On applying this boundary condition, your left hand side will be fx, your left hand side will be fx, and your right hand side, in the right hand side we have to put y equal to 0, so we will have sin n pi x upon 10. So from here you can see that therefore our Bn will be 2 upon L. L means the length of the strip is 10, 0 to 10. Fx means your value of ux naught into sine n pi x upon 10 into dx. So now this will be over 1 by 5, then 0 to 10. Now 0 to 10, for 0 to 10 fx has two values, one for 0 to 5 which is your 20x into sine n pi x upon 10 dx. Then the second value will be from 5 to 10. In this case our value is 200 minus 20x and then sine n pi x upon 20 into dx. Now let us integrate this one. So this is equal to 20 x, integration of sine will be your minus cos n pi x upon 10 into 10 upon n pi. Then we will have minus sign, differentiation of x will be 1. Again the integration of this bracket will be sine n pi x upon 10 into 100 upon n square pi square. Then the limits will be from 0 to 5. Then we will have plus sign. Then the second bracket, here we will have 200 minus 2x, integration of sine will be minus cos n pi x upon 10 into 10 upon n pi. Then we will have minus sign, the difference of this one will be minus 2 and integration of this one will be sine n pi x upon 10 into 10 whole square, that means 100 upon n square pi square. So now on simplifying this integration, on solving, I am not going in this calculation. For this we will have to put x equal to 5 and here we will have cos n pi by 2. Cos n pi by 2 can be either 1 or 0, but after solving these terms we will get 4 into minus 50. I am not going in the calculation, so you can simplify it. So we will get this term, then we will get 100 into n square pi square into sine n pi by 2. Then we will have plus 50 upon n pi into cos n pi by 2. Then again we will have 100 n square pi square sine n pi by 2. And this calculation is not quite tough, so you can do it. So now you can see that this term and this term is cancelled, so this will be 200 and hence 800 n square pi square into sine n pi by 2. Now if n is even, then you can say that this will be your even multiple of pi. So you know that sine n pi is 0, so that will be your 0. Now if n is odd, then this will be your minus 1 to power n minus 1 by 2. Now if n is odd, then this will be your sine pi by 2. Sine pi by 2 is plus 1. You can see from here, if your n is 1, then this will be minus 1 to power 0 and that is 1. So this is your if n is odd. So thus our solution is, your solution was Bn means 800 upon n square pi square minus 1 to power n minus 1 by 2. Then we have the term of sine n pi x upon L, that means 10 into e to power minus lambda, that means n pi upon 10 into y. So this is your solution of the Laplace equation. So thank you so much for attending this lecture. Now for my side, this application of the partial differential equation is over. Now if you have any problem related to the one-dimensional heat equation, one-dimensional wave equation or two-dimensional heat equation, please comment me in the comment box. I will try to solve those questions or will try to solve your query. Thank you so much.